evaporator coil selections. Of course, again, fin and tube designs. So I like the hourglass as a metaphor, because you need to consider as many factors as possible, and then your ultimate choice is hopefully going to be widely applicable. No? So you need to take as much into account as you can, as much information as you have regarding the selection that you're making. And we're going to make selections from standard product range. Okay, so you will see in any catalog, not just thermocoils catalog, any catalog, there's nominal duties listed. So nominal duties are multiplied with specific factors, and then you get to the value that you're ultimately after. And it's basically, for the greater part, as evaporators is concerned, divided into low temperature and medium temperature conditions. No? So I'm just going to use the thermocoil criteria. Obviously, it's very similar for other suppliers. So 4 millimeter fin spacing is the norm for medium temperature conditions. How did we arrive at 4 mil? It's a good balance between the duty and, of course, the cost. So the more fin area you have, the greater the cost, because you use more material. Okay, 7 millimeter kind of is necessitated for low temp, because you have an ice buildup, and it obviously becomes restrictive and it starts blocking the airflow. So low temperature conditions tends to lean towards a wider fin spacing. Okay, so the main factors that influence accurate selections basically is, are you starting off with an accurate heat load calculation? Huh? So that in itself is a week-long course that we can have, and lots of discussions there, but basically your heat load calculations is crucial to start off with. If you start with bizarre figures there, then you can do the rest perfect, but your results might still be very lacking. And like everything in our industry, use the feedback, apply an approach, use the feedback from your installation, and then that can help you to fine-tune ultimately what you do. It's really useful to see how well your plans worked out. And of course, the refrigerant that you're using. Huh? So sometimes I get someone that's looking for an evaporator, and they want to connect it to a split aircon unit that they salvaged from someplace. So the refrigerant very much affects the duty of the evaporator. Operating temperatures. So is it a freezer room that they sometimes want to turn into a cold room? It's really bizarre what some people do sometimes, but obviously your operating temperatures is crucial. And the difference in temperature between your suction conditions that you have and your control temperature. Control temperatures is normally return air. Right? So most systems control based on return air. So that will be the warmest air in your room. So yeah, that the RH, that's quite important. If you don't keep an eye on the relative humidity in the room, remember, any cooling process dehydrates the air. If you cool the air, you dehydrate the air. And that results in, of course, in a lower humidity in the room. If you've got carcasses hanging there, the carcasses will dehydrate. No? So the moisture in the carcass will migrate into the lower vapor pressure of the air, and slowly but surely you'll dehydrate the product that you have in there. You have a customer that is storing blueberries. You have a room half the size of this venue, and they might have 4 million rands of blueberries in there. If they lose 10% in a few days, that's a lot of. So it's very relevant to keep one eye on the RH. So there's a scale there that you can look at in the thermocoil catalog, and that will give you an idea of what the RH will be with the delta T. So the suction temperature that you want to operate at, Okay, and then you have some evaporator material options. So some people call it inner groove tubing, some people call it rifle bore, but basically it's a tube that has got an increased surface area on the inside and it offers you higher capacity. Stainless steel tubes is also an option. Aluminium fin is very common. Coated aluminium fin, hydrophilic coated, that's what we call it. You could have copper fin. So, and there's also a aluminium magnesium, which is a hardy type of aluminium used in marine applications. Casing, of course, you know, it's sheet metal. You can have it from aluminium, you can have it stainless steel, you can have galvanized casing as well. Okay, so if you've been lost so far, does that picture help you? No? It's those things in the top of the corner in the cold room. That's called an evaporator, and I'll run you through the thermocoil catalog, but just spend some time. If you have another supplier, read their instructions, read their in most cases everyone does it in a most basic way possible. Okay, so let's say you have a cold room and it's connected to a condensing unit. Okay, there's your compressor and your condenser. It's medium temperature and your room needs to be 0 degrees. Okay, so that's your control temperature. So a good suction temperature to design for is -8. Okay? That difference between the room temperature and the suction temperature in the region of 6, 7, 8 degrees Celsius. No? So you have freezer rooms, also very common in the retail sector. And there's your condensing unit, -18. If you want to store fruit long term, -18 or colder. Huh? The enzymes stay active. And of course your product will deteriorate if it's -15, -14 even. Huh? So, okay, and that's typically referred to in the retail sector as low temperature, of course. All right. Sorry, which way am I going? So your suction temperature there is very commonly -25. Okay, you can certainly operate the compressor at -35, but obviously that consumes more electricity. No? So if you're generating it with diesel, then obviously it makes sense not to operate the compressor at a lower suction temperature if it's not required. Right, that chart, that sliding scale there. So you'll find this in the thermocoil catalog, but basically all this is look at the scale at the bottom there, and that is of course your temperature difference between suction and air on. And then look at the vertical scale there, that's the RH. So very common is to aim for about a 7K delta T. So between 7 and 8K, that's most common. Then you get best value for money with your evaporator, and of course it's what the industry uses as a norm. Just take note, if you want to operate at a delta T lower than 7K, generally you need an electronic expansion valve. Simply because a thermostatic valve can't handle that close, that small delta T as effectively. It certainly will work, but just be on the lookout for issues there. Okay, so that's a page you'll find in the catalog. Everyone else does it. Everyone does it in their specific way. We're going to look at the calculations to get to the nominal duty. Okay, so nominal duty. So look at that formula there. So your nominal duty is your evaporative capacity that you want divided by F1. F1 is your correction factor relating to your refrigerant that you're using. F2, the material of your evaporator that you're choosing. Remember, we can build an evaporator with aluminium fins or with copper fins. No? Okay, so very easy formula, primary school maths hopefully. And let's look at, so that's a bit bigger, But you see, your correction factor, when you're using 404, of course, is 1. No? The nominal duties that you see in the tables is based on 404. If you were sitting in this venue 20 years ago, the nominal values would be based on R22. Huh? Who can recall that? Okay, so a few of us. So R22 was the norm 20 years ago. Everything was published, the nominal duties was published in R22. Today it's 404, it's an HFC. And of course, 134A is commonly used. If you have a system where maybe you replace something old, there's a value for R22 as well. Okay. That's where that comes from. And of course, your F2, that's your material correction factor. Then it's also handy to start off with what kind of evaporator do you need. They're mostly ceiling mounted. The service guys, they love these angular units. And the difference here is, so what's handy about them is you open the cold room door and you look at the coil and you can see the fin. And if there's ice on the fin, you know to go pay attention to it. No? Whereas with, because obviously over here your inlet, your warm air enters at the angle at the back and your cold air exits on the face of the coil. So that fan forces the air through the coil. And of course now you can have the evaporator quite close to the corner of the room. Né? Sometimes a bakery cold room or bakery freezer room, it's 1.2 meters by 2 meters. Some of these rooms are really small. So there's not lots of space for the return air to get back in. So that's a very popular range. That one, side view of the most common units. So in that case, obviously, fan draws the air through the coil. Warm air enters the back. So now, if this coil is iced up, you got to get past all the pallets, né, on the slippery floor. Né, try and make your way to the back of the room to try and see if the coil is iced up. Because it ices up on the inlet side. Right? So it's not visible. If you open the door, you can't see if the coil is iced up. You have to walk in. And most, if you get to some of these supermarkets, you can barely move, the day before Black Friday. Because the room is completely filled with stock. Then another common type is the dual discharge. So dual discharge, draw air in the center, discharge on the sides. Sorry, that's actually 2 coils. So you have 2 evaporators, one left, one right, and they are suitable for specific applications. Let's do an example. Heat load 3.2 kilowatt. You want the room temperature at 0. Your refrigerant is 134A. There's your formula, 134A. There's your aluminium fin. You want to use the cheapest thing possible. And that's your result. Okay, so your nominal value changed from, you start off with 3.2, you apply the specific application criteria. So your coil that you're looking for in the nominal value table is 3.5 kilowatt. Okay, there's a quick reference table. You can use that, or you can go through the catalog. So what were we looking for? 3.5, huh? What was it, sorry? 3.51. Okay, there's your table. Okay, so you see this one does 3.4. I'm happy with that. Who's happy with that? Huh? Doesn't have to be, always have to be bigger. Maybe the 3.2 kilowatt that you started off with is already a conservative value. Nah? It's not necessary to add cheese on top of cheese on top of cheese on top of cheese. Nah? Otherwise, there's no cheese left tomorrow morning. So you apply what works for you. You obviously have to develop that intuition. Sorry, it's this kind of coil. A TEB 031 E14. Okay, so that's a single fan unit. Maybe you want 2 fans. Now, some guys prefer 2 fans, so if one fan breaks, at least there's another fan running. What generally happens, if the second fan breaks, then they go fix both fans. So that's generally the case, but they'll tell you they want nothing, nothing with one fan. Okay, so you can choose. Of course, if you're going to select something with 2 fans, hopefully it makes sense that you're going to then end up with something a little more costly, of course. Nah? But this is sometimes a criteria that's laid down. Okay, there's a low temperature application, a freezer room, 1.35 kilowatt, maybe a bakery freezer. Huh? Every supermarket's got a bakery freezer. Okay, minus 18, refrigerant is 404. There's your formula again, 404, aluminium fan. Okay, there's your result, 1.35 kilowatt. Okay, so nothing changed. All right, but remember, the tables is developed for 404. And the tables is also developed using aluminium fin. Okay, so just apply that formula. And of course, in this case, 1.35 kilowatt. Okay, so I think that one is suitable. The TEMB is this, it's that angular type. Huh? And sometimes you have a prep area in a supermarket where they pack meat or they pack vegetables. So that typically operates at warmer conditions. Nah? So you can't expect people to stand and pack meat in the cold room at 0. Huh? They're not going to tolerate that for too long. So some of you use R507. And let's say your set point in the room is 12. It's quite cold, but it's quite common for prep area. Okay, so again, look at your scale there in terms of your humidity and your delta T. Right, so if we apply a delta T of 8K, we want the room at 12. So 12 minus 8 is what? Okay, plus 4. Okay, so basically you want an evaporator then to operate at plus 4 suction temperature. And maybe you connect it to a multiplex system. So big mistake sometimes happens is folks forget to fit a device called an evaporator pressure regulator. Your coil is supposed to operate at a suction temperature of plus 4. Your system is operating at a suction temperature of minus 8. If you don't have the evaporator pressure regulator, this coil will have a suction condition of minus 8, and that coil will offer significantly higher capacity. So then your prep area will be nice and cool, but you'll be wasting obviously a lot of energy in your plant room. So please consider that evaporator pressure regulator, because that's quite a common thing that the folks don't keep track of. Again, there's your table, your quick reference table. You want the dual discharge there, because you don't want the cold air blowing in the ladies' necks. They're going to complain. You're going to go deaf in one ear. They're not going to like that. So the prep areas, the dual discharge coils is more popular. They are more costly, but they offer the benefit of that you don't have a very strong breeze on the folks in the packing area. Okay, so what were we looking for? What kind of duty? 6.2. Okay. All right, there we got 5.1. It's a dual discharge, TEDB. That's too little. I'm going to go for the 8.6. Okay, again, that's how you choose them. Maybe you can go to the dual discharge page, but that's basically all it is. Okay. Any questions?
Waiting for chilled water.
Chilled water, okay. All right. Condenser selections. Yeah, sure.
How did you get to the 8 degrees?
The 8. The delta T of 8.
Lower than the room temperature.
Well, it's just a combination of economy versus cost.
You wanted the TEDB.
Sorry.
You wanted the TEDB.
Yes. So, sorry, we go back. So there, it's a meat packing area. I wanted the dual discharge. No? So that the difference of 8 is what is a good combination of economy, of course, and then it also is a case. It's also a case of that you you want to. The 8 offers you an economy, but it also means that your system is still effectively functioning. I don't know if that answers your question.
So if I take it to 5,
You can, yes.
will it make a difference?
It will. Yeah. So if you take it to 5, you're possibly going to need a higher surface area. And the 5, maybe you want at 5 because at 5 your dehydration tempo is going to be lower. But don't kid yourself. Even if you change it to 4, you will still dehydrate the air. So and also the 8, the 7 and the 8 is to offer you a room conditioner with an RH of around 80, 75 to 80. So depends on what you want to, of course, keep your product at.